Hey guys, so this is Winter 23, paper 22. This was assigned to you as your homework. Let's get right into it. So first question, velocity is a vector, speed is a scalar. State how a vector differs from a scalar. Again, it's pretty straightforward. Vector has direction, whereas a scalar quantity doesn't. Next part, underline all the vector quantities in the list. Acceleration is a vector, distance is a scalar, energy is a scalar, mass is a scalar, momentum is a vector, temperature is a scalar again. Part C, 1.1 shows a passenger running across a large ship at right angles to the direction in which the ship is moving. The passenger runs across the ship at 2.4 meters per second due north. The large ship is traveling due east at 6.8 meters per second. Determine either graphically or by calculation the resultant velocity of the passenger. Give the direction in which the passenger is moving relative to due north. Show how the answer is obtained. Now in this question you have a choice of either doing this by drawing. I generally tend to avoid doing this by drawing because of the potential errors that could be involved. I'll instead just be using trigonometry here. So he's moving north, the ship is taking him east, so he'll be moving in a direction like this. So he's also going to be moving north and also going to be moving east. So I also am told that these are perpendicular to each other. So if this is my 2.4 due north, this is my whatever this vector is due east. Right, so these are the two things that we have here. So it's this and this. So there's this vector which is 2.4 meters per second and this one is 6.8 meters per second. Now you can also do this, that you can pick one of these up and take it here, so you can see that it's going to be like this. Now the head to tail rule will be obeyed. So you know that the resultant vector will be along this direction. Like this. This is going to be the resultant vector with this vector superposed here. Right, so it's going to be like this. So I know that because of this being a right angle, this is also going to be a right angle. And because the answer is asking me for the direction in which the passenger is moving relative to due north, so I know that the examiner is basically asking me for this. And if I look at this triangle, it's also going to be the same as this angle, right? Let's call this alpha. This is what I have to find out. So for the magnitude of the velocity, I'll just use Pythagoras theorem. So the resultant velocity is going to be 2.4 square plus 6.8 square, right? The longest side, this V, is what I need to find, which is the hypotenuse of this triangle right here. So when I find this out, this velocity turns out to be 7.211. So 7.21 correct to 3 or 7.2 correct to 2 SF meters per second. And then we need to find this angle. If I think about this angle, so I know the adjacent to this and I know the opposite. I'll try not to do this because there is a possibility I could have made an error in finding this. So that's why I'll choose to work with the values that the examiner has given to me. Now if I think about my trig ratios, this is going to be tan, which is opposite. So 6.8 over adjacent, which is 2.4. So tan inverse 6.8 over 2.4 is 70.5599. So again, if we do this to 2SF again, this is going to be 71 degrees. Two, a spacecraft of mass 300 kg is moving in a straight line in space at a speed of 8,000 meters per second. Calculate the momentum. Again, always first write out the formula. P equals mv. Mass is 300, v is 8 1000. So this is going to be 2.4 million, right? So 2.4 into 10 to the 6 meters per second, kg meters per second. The fuel on the spacecraft explodes and the spacecraft splits into two parts. The direction in which the parts move does not change. After the explosion, the speed of the front part increases to 9,000 meters per second. It has a mass of 150 kg. Calculate the speed of the rear part after the explosion. So they're telling you that this was the entire rocket first, and now this splits into two parts, right? And you calculated the momentum of the combined object at first. Now this part, this rear part, you are not given its mass, but you can find this out, right? Because the spacecraft had mass 300 kg. If this one, the front part, has a mass of 150, then this one would also have a mass of 150 kg. And then this part would also have a mass of 150, right? Additionally, we are told that the direction in which the parts move does not change. So how they were moving previously like this, they're still going to be moving in the same directions. So the speed of the front part increases to 9,000 meters per second. And now we need to find out what this velocity v is. Again, we'll use the conservation of momentum, that momentum or total momentum before. Actually, let's write this in a more concise form. In your exam, it should be really clear that what exactly are you using. If the examiner gets the indication that you are using the conservation of momentum, you'll get 1 mark just for that. This is why you need to be super clear with your working. So total momentum before equals total momentum afterwards. So total momentum before, you just found out. Again, here there are no changes in direction, so we won't have to use the sign convention. How it was moving previously is how all the velocities are afterwards as well. So it's 150 times v plus 150 times 9,000, right? Now we just rearrange, we take this here, subtract, and the answer of that we divide by 150. So this v turns out to be 7,000 meters per second. Total kinetic energy of the two parts after the explosion is greater than the original kinetic energy of the spacecraft. State the energy transfer that occurs in the explosion. So here, this might seem a bit odd to you why the total kinetic energy afterwards of the explosion is greater, and the reason for that is because of the explosion of the fuel, right? So state the energy transfer that occurs in the explosion. So there's the chemical potential energy in the fuel which is transferred to the kinetic energy. So I'll say the chemical potential energy, which you know is often asked as being stored in batteries or fuels. So chemical potential energy causes the increase in kinetic energy. So this is not like a normal explosion or a collision where a car hits a wall, because there is nothing which is going to increase the energy, because you know that in doing so the energy is given off as heat and sound. But in this case, the fuel actually increases the kinetic energy. The explosion lasts for 0.2 seconds. Calculate the average force on the front part. So force is rate of change of momentum. So we know the momentum before, we know the momentum afterwards of the front part. So before, the front part was moving at 8,000 meters per second as a part of that original rocket, right, of that original spacecraft. And then when it separates, it now is traveling at 9,000 meters per second. So it's very easy for me to see what the change in momentum is. If I think about change in momentum as mv mass times final velocity minus mass times initial velocity. This is very easy to see now. So mass was of the front part was 1500, final velocity is 9000 minus 1500 times 8000, the initial velocity, divided by the time, which is 0.20 seconds. All right. Now you guys can also probably see that you could have factored out the 1500. That's perfectly fine. As you can also see from this algebraic expression here that you can factor out the m. So m times v minus u. So 1500 times 9000 minus 8000, you could have also written that. And then you just divide that by 0.2. So this turns out to be 750,000, which you can also write as 7.5 into 10 to the 5 newtons. Let's have a look at question 3. A plain irregular lamina has a mass of 50 grams. It hangs from a nail that passes through a small hole H near to the edge of the lamina. So H is the hole. The nail acts as a pivot and the lamina can swing about it. The lamina is held in the position shown in 3.1, a small distance above a horizontal bench. So it's not freely suspended, rather it's held in position right now. The center of gravity of the lamina is at G. So there's this weight which we know is going to create a turning effect about this pivot H, right? Because it's hanging from that point. The nail acts as a pivot. So the center of gravity is G. The weight of the lamina is a force that acts downwards. Explain why the lamina experiences this downward force. So you know this is because of the weight, right? Now it asks why does it experience this downward force? So you can say that the earth pulls the lamina towards itself, right? That is how the weight arises. Or another way to also say this is to say that the lamina is in the gravitational field of the earth. So the lamina experiences the gravitational force of attraction exerted by the earth on the lamina. Calculate the weight of the lamina on earth. So what do we know here? What do we know? So yeah, the mass of the lamina is given as 50 grams. So you can find out the weight simply by using W equals mg. So 50 over 1000 times 9.8. So this turns out to be 0.49 newtons exactly. Next part. The weight produces a moment about the pivot through H. Using 3.1, calculate the moment of the weight about the pivot. In questions like these, you can see a lot of distances labeled. So you know that the center of gravity is where the weight appears to act through. So this is that point. This is the actual pivot. Now out of these three distances, which one do you select for the calculation of the moment? Here you need to take into account the very definition of moment, which is that it's the product of force and the perpendicular distance from the pivot. Right now, this distance, if I take this in a straight line, does not appear to be the perpendicular distance. To find out what this is, I can actually extrapolate the line along which this force acts. This is known as the line of action of the force. And now this will enable you to see what the perpendicular distance from the pivot is. So this is the pivot. This is that entire line of action of the force. You know from math as well that the perpendicular distance is always the shortest distance. So all you need to do is from this line you find the shortest or the perpendicular distance. So this is what you really want, 8 centimeters, right? So you extrapolate the force to find out the direction along which this acts, and then you take the shortest perpendicular distance from it. So 8 centimeters times the weight that you just found out. So it's going to be force times perpendicular distance. So 0.49 times 8, but that was centimeters. So 10 to the negative 2 because if you look at the units, you need the answer in Newton meter. This turns out to be 0.039 Newton meters. The lamina is now released from the position shown in 3.1. Describe what happens to the lamina from the time it is released until it stops moving. So we know that the moment here, what we just calculated, this right now is creating a clockwise moment. So it will cause the lamina to swing like this, and then it will keep swinging, but gradually slowing down until G is directly below H, right? Why would it come to rest in this position? Because otherwise, if it's not in this position, it's going to keep creating a moment. Right now, it's going to create a clockwise moment. But as its momentum swings it through this vertical position, it would create an anti-clockwise moment, hence bringing it back. And then it's going to keep slowing down until we are directly below H. Because at that point, no more moment will be produced by the weight. So describe what happens to the lamina. So first off, I'll say that the lamina drops clockwise. Then I'll say that as it swings, it gradually slows down. And then lastly, it comes to rest at a position with the center of gravity G directly below the pivot H. Notice how this time out I'm not saying the center of gravity or the pivot, because these are symbols that have been already defined by the examiner. So I don't need to define them again. So I can use the symbols that the examiner has used in the questions. Question 4.1 shows a long vertical tube sealed at the base and open at the other end. The tube is 1 meter long. The cross-sectional area of the tube is 4 into 10 to the negative 4, and it is filled with a liquid of this density. Atmospheric pressure is this much. Calculate the total pressure in the liquid at the bottom of the tube. Always remember that if you are explicitly told to calculate the total pressure, you would have to add the liquid pressure and the atmospheric pressure. So first off, let's find the liquid pressure. So that's rho GH. So rho was given as 1.4 into 10 to the 4. G is 9.8 and the depth is 1. So this turns out to be 1.4 into 10 to the 5 pascals. When you add this to it, because you want the total pressure, this would turn out as 2.4 into 10 to the 5 pascals. When the examiner just wants you to use rho GH, they'll say the difference in pressure between the top and the bottom, or they'll say the pressure due to the liquid. But if it says the total pressure, then you need to add to the liquid pressure the atmospheric pressure. Force exerted on the inside surface of the bottom of the tube. So we have the pressure. So the pressure acts in all directions. We can just find this out, that because of the pressure acting on this area, what's the force? So since pressure is force over area, force is pressure times area. So the total pressure times the area, which was 4 into 10 to the negative 4, this turns out to be 95 newtons. Actually, this is 96 newtons. And again, we don't need to write the unit. It's already given. Next, part B. A small sheet of glass is placed over the open end of the tube. The tube is inverted in a container of the dense liquid. Open end of the tube and the sheet of the glass are a short distance below the surface of the liquid. 4.2 shows this arrangement. Sheet of the glass seals the open end of the inverted tube. So if you look at this, by the way, you should recall that this is how a barometer is formed. So we are making a barometer out of this liquid. Describe what happens in the inverted tube when the sheet of the glass is removed. Now you know that the liquid in the tube will fall out. Tube falls, but it's only to a certain level. Right? Because you know that after a while, when the liquid reaches a level like this, you will have a vacuum all of here. So how does the liquid know when to stop? Vacuum is a single C. So when does the liquid know when to stop? That's when the external atmospheric pressure equals the liquid pressure of the tube, right? So it falls to a certain level, and then this creates a vacuum at the top. The final liquid level in the tube is such that the liquid pressure equals the atmospheric pressure. That is how we use the height of this liquid column to find out the atmospheric pressure in an actual barometer. So that's this. This equipment is used to make a measurement that is used to calculate atmospheric pressure. Describe the measurement made and then use it in the calculation of the atmospheric pressure. You may draw a diagram to help your description. So as with the diagram that we just made, you also know there's going to be the tube here, and let's say this is the liquid level here, right, with the vacuum here. So you know that the liquid is in all of here. So remember that you need this height from the liquid level in the dish as far as it goes up in the tube. So when you measure the height, as shown. Now if I didn't make the diagram, I could have also said that this is the height from the liquid level in the dish all the way up to the liquid level in the tube. But I don't need to say this because I've shown this using the diagram. And then use rho GH to calculate pressure. And again, because as we just wrote down, the liquid pressure and the atmospheric pressure will be equal. So that's how you get the atmospheric pressure. Rho GH gives you the liquid pressure. In that case, it's also going to be equal to the atmospheric pressure. 5.1 shows a device that cools the air in a room by evaporation. Water drips from the container into the sponge block and keeps it wet. Air flows in through one grill and out through the other. As the air flows through the wet sponge block, the water in the sponge block evaporates. When the water evaporates, the temperature of the water remaining in the sponge block decreases. Explain in terms of the movement of particles why this decrease in temperature occurs. So this is in your syllabus by this, and in your syllabus it says that explain how evaporation causes a cooling effect. This is stuff that you know, it's very basic, which is that the evaporation takes away the fastest moving particles. So fastest moving particles escape in evaporation. So the particles which are left behind have lower kinetic energy. So particles left behind have less average kinetic energy. And again, because the kinetic energy is less, this causes the temperature to decrease. Right? This is how you explain the cooling effect. Explain why energy is needed when the water evaporates. So obviously, for those fast moving particles, you need to give it energy so that they can do work against the forces of attraction and escape. So work needs to be done against intermolecular forces to escape. State two ways in which evaporation differs from boiling. So you can say, you can take your pick from like 3 or 4 different points. So boiling forms bubbles, evaporation does not. You can also say that evaporation causes a cooling effect, boiling occurs at a constant temperature, like any state change. Whereas evaporation causes a cooling effect. Then you can also talk about how boiling is not affected by factors such as surface area, the movement of wind, but evaporation is. Question number 6. Loudspeaker shown in 6.1 produces a sound of frequency 800 Hz. State what is meant by frequency. Again, you can define this in a number of ways. So frequency, you can say, is the number of waves or the number of crests or the number of wavelengths produced per unit time. And again, another way to talk about this very definition is to say that instead of production, you say these are the number of crests or wavelengths passing a point per unit time. Both of these are correct. Explain whether the sound produced by the speaker is audible to a human with healthy hearing. So this is 200 Hertz. The audible frequency range is 20 to 20,000 Hertz. So since this lies in that range, yes, it is audible. It lies between 20 and 20,000 Hertz. Part C, describe the motion of the cone in 6.1 and explain how this causes the production of sound. So this is that moving coil loudspeaker, right? So you know how to describe the production of sound using this. So you know that the way that this loudspeaker is, because of that magnetic field and whatnot, even though that's not really asked here, but you know that that alternating power supply makes the magnet move forward and backwards to which the cone is connected, and as the cone moves forward and backwards, it creates compressions and rarefactions, right? It makes the particles vibrate as well. You don't need to talk about that magnetism and electricity part here. You can just say that as the coil, and because of that the cone vibrate, they make the air molecules move as well. By creating changing pressure in the air. And in doing so, it creates compressions and rarefactions. And then we can say that this causes the air molecules to vibrate. All right. The sun is a very large and extremely violent ball of gas. Electromagnetic radiation from explosions on the surface of the sun reaches the earth. Explain why sound from explosions on the surface of the sun does not reach the earth. This is very easy. You know that sound is a longitudinal wave, and like all longitudinal waves, it needs a medium. So it cannot travel in the vacuum of space. Alright, all longitudinal waves need media, but transverse waves, especially the electromagnetic waves, do not need media. Right? They can be transferred in vacuum as well. Alright, next one. An electric circuit contains a battery, a fixed resistor R, and a voltmeter and a thermistor. 7.1 is an incomplete diagram of the arrangement. The thermistor is connected between T1 and T2. Complete 7.1 by drawing the circuit symbol for a thermistor. So a thermistor is pretty much like a resistor, as is an LDR. But to show the variation with temperature, you basically have that part of the heating curve, right? Remember how a heating curve is drawn like this? So that's part of that. The resistance of R is 2.5 ohms. Reading on the voltmeter is also given. So finding the current in R is not that difficult. We just use V equals to IR. So I equals V over R. So V is 0.4, R is 2.5. So I turns out to be 0.16 amperes. Power transferred in R. Now for R we know everything. You can use any formula that you want. Let's use VI. So voltage across R is 0.4. Current through it is 0.16. So this turns out to be 0.064 watts. Temperature of the thermistor increases. Explain what happens to the reading on the voltmeter. The next part asks, the temperature of the thermistor increases. Explain what happens to the reading on the voltmeter. So the reading that was taken was across this resistance voltmeter, right? So I can very easily use the voltage divider argument. If the temperature increases, then I know that the resistance of the thermistor is going to decrease. And then I can say that now the resistance of the thermistor is a smaller fraction of the total resistance. So the voltage across it, by the voltage divider argument, the voltage across it is also going to decrease. Let's go on to question number 8. So 8.1 shows a permanent magnet attached to one end of an unstressed spring and held at rest just above a solenoid. The solenoid is connected to a sensitive ammeter. State the name of a substance from which permanent magnets are made. So we know that permanent magnets are made of steel, just like how temporary magnets are made of soft iron. The magnet is released and moves downwards towards the solenoid. The ammeter shows that there is a current in the solenoid when the magnet moves. Explain why there is a current in the solenoid. So we know that as the magnet falls, the field lines will be cut by the coil. And this will lead to a change in the magnetic flux in the solenoid. And then this change in magnetic flux will cause a induced EMF. And since this induced EMF, again remember that this question is asking about the current. So there is an induced EMF basically by Faraday's law, which causes an induced current in the closed loop. So when you are asked for the induced, when a current is going to be produced, then you need to say that inside that closed loop, the induced EMF is going to cause the induced current. So in cases where the current is asked, you do need to go one step further. The current causes the top end of the solenoid to become the S pole of an electromagnet. Bottom end of the permanent magnet is an S pole. Explain why the top end of the solenoid becomes an S pole as the magnet moves downwards towards the solenoid. You know this has to do with Lenz's law, that because of this S, this end is also going to become an S pole to basically oppose the change which created this EMF. This is Lenz's law, right? So you will say that by Lenz's law, the direction of the induced EMF or rather I can also explain this by the current, that the direction of the induced current is as to oppose the falling of the magnet downwards. Or rather than oppose, I should say repel. That just makes more sense. As to repel the magnet falling down. The magnet oscillates up and down. Describe what happens to the current in the solenoid. So basically when it's going to move down, it's going to create an EMF in a certain direction. When it goes up, it creates an EMF in the opposite direction. So it basically induces a EMF which is also changing in direction and in magnitude. So the current also varies in magnitude and in direction. So the current and EMF, actually because it's asking about the current, let me first explain that the EMF and hence the current vary in direction in magnitude. Next question. In space, an interstellar cloud of dust and gas collapses to form a protostar. The cloud contains hydrogen. Describe the energy transfers that take place as the cloud collapses and forms the protostar. So we know that it collapses under the effect of its own gravity. So the gravitational potential energy causes it to collapse, and then as it collapses inwards because of its gravity, that turns into the kinetic energy as the molecules move faster inside that cloud, and then ultimately it turns into internal or thermal energy, which causes the temperature of this cloud to go up. The collapse results in a nuclear reaction in the protostar that involves the isotope hydrogen 3. The isotope is radioactive. It decays by beta particle emission. State how the nuclei of isotopes of the same element are different. So we know that they have the same number of protons, but since the question is just asking for what's different, you can say different number of neutrons. Explain why hydrogen 3 cannot decay by alpha particle emission. Well, this is pretty obvious because H is 3, 1 and it can't emit 4 nucleons when it just has 3 nucleons, right? And also because of the number of protons, so you can say that not enough protons and nucleons. Complete the equation for the decay of hydrogen 3 to an isotope of helium. So I know beta is 0, -1, right? And helium is going to be, so it's 1 here, so -1 plus something should equal the 1. So this should be a 2, and similarly this should be a 3, right? So this is the decay equation. Again, some of you might be thinking that it should be hydrogen, it should be helium 4 but again it's an isotope. You should work of the information that you definitely know it's going to be true, which is the configuration of an electron, and then you should figure out what you don't know by the conservation of nucleon number and the conservation of proton number. Explain how the nuclear reaction in the protostar stops further collapse as the protostar becomes a stable star. So you have to explain this in terms of the forces. So we know that the nuclear reaction in the core that was just described above, this produces an outwards force, or you can also say an outward pressure, because of the high temperature. And the gravitational force is inwards, and a star becomes stable. So this becomes stable when both of these forces are balanced. When the inward force due to the gravitational force and the outward force due to the high temperature, when these are balanced, when these are equal, this is when a star becomes stable. The cloud of dust and gas also that collapses also contains atoms of some of the heaviest elements. State which part of the life cycle of a star is responsible for the production of the heaviest elements. Remember that the heavy elements are only produced with the high mass stars. So as a red supergiant stage of the high mass stars, as it explodes in a supernova, this is when you have the heavier elements forming, right? So the carbon is then fusing together to give you iron as the heavier elements. Question 10. Isotope iodine 131 emits 2 types of radiation. Gamma is one of the types emitted. A sample of iodine 131 produces a narrow beam of radiations which passes into the magnetic field. 10.1 shows some of the paths taken in the magnetic field by the radiation. The direction of the magnetic field is into the page, as we know the x's represent. Mark with a gamma symbol one of the paths taken by the gamma radiation. So obviously gamma is undeviated in electric and magnetic fields. Determine the other type of radiation emitted by iodine 131. Now for this, I'll need to use the left hand rule, because I can see that since they are being deflected downwards, so it must be, what do you call it? So the force must be downwards. And the magnetic field is into the page, so my first finger must be into the page. Now when I do this, I find that my middle finger, which shows the direction of the current, points to the left. Now only negative particles have the direction of current opposite to how they are moving. Because if this was an alpha particle, we would say that the finger should have pointed towards this direction, and that is what would also be the current, because for positive particles, how they move is also the direction of conventional current. But because now my middle finger is pointing opposite to how the particles are moving, I deduce that this must be a beta particle. So this is beta radiation. So the explanation is using the left hand rule, using Fleming's left hand rule. The thumb points down and the first finger points into the page. So what we find is that the second finger points to the left, which is opposite to the movement of particles. So if the conventional current is to the left, then it must be a beta particle, right? So this must be negative particles. All right, next one. In another experiment, the beam of radiation from the sample is incident on a 5 millimeters thick sheet of lead. State what happens to the other two types of radiation in the beam. So we know that 5 mm thick sheet of lead is actually not sufficient to block all of the gamma, but we know that beta would be completely blocked. So beta is completely blocked or absorbed, but some gamma may penetrate through. All right, next one. Gamma radiation produced has a frequency of this much. Speed of EM radiation is given. You just need to find out the wavelength. Very easy. V equals F lambda. Lambda would be V over F. So 3 into 10 to the 8 divided by this frequency 8.8 into 10 to the 19. So this is 3.4 into 10 to the negative 12 meters, correct to 2SF. So that's it for this paper. See you in the next one.